Okay, guys, we're finishing chapter 8 today. This will be the last day of notes for that. I feel like tomorrow we should have like an extra practice kind of a day, maybe do a write up that you guys could turn in, and I can grade while you guys work on review stuff on Wednesday. That's kind of where I'm at right now. Those of you who are at home on Tuesday, the A Day people, maybe what I'll need you to do is type stuff up and send it in so I could grade it that way. Okay, here we go. Comparing the normal distribution with what we found on the last day, the t-distributions. When n is low, like n equals 4 from our day 1 of these notes with that activity we did, the t-distribution has a lot more area in the tails of the distribution, and therefore, of course, less values in the center. As n increases, the t-distribution shape gets closer and closer to being the normal shape. It never gets there. It approaches it like it's an asymptote. Now, you guys have studied vertical asymptotes, and the graph gets closer to a vertical asymptote. That's a linear asymptote. Well, here the asymptote would be the normal curve, and this t-distribution is just getting closer and closer to it, if you can visualize that. Now, I know we talked about this, but I just want to have it in your notes somewhere instead of just something that I talked about on the board. So I'm going to do a rough sketch of the following 3 distributions on the same x-axis. The standard normal curve, so that's from -3 to 3. So I'm just gonna do a regular old normal curve. That's my version of the normal curve today. The t-distribution with n equals 4, as we did in our example, so that'd be the t3 distribution. And so I'm just gonna go really wide and not very tall in the middle, right? So that's what we'll call that the t3 distribution. Not necessarily accurate. What we could do if we wanted to be more accurate with that is we could do an inverse t for degrees of freedom 3 and find out how far we'd have to go to be 99.7% confident. Because with the normal curve, that's about 3 standard deviations, isn't it? And so we could go inverse t with degrees of freedom 3, and then we could figure out where this is supposed to look like it hits the axis. But I'm just drawing this to give you guys a general feel, right? And then we'll go with a n equals 15, so that would be the t14 distribution. That's going to look closer to the normal curve, so it's going to have to hit in between where these two do. And then let's see, maybe get a little taller in the middle, and then it's got to sneak underneath that other t-distribution. So not a great drawing, but you guys get the idea of what we're doing here. An inference procedure is considered to be robust if it gives fairly accurate results even when a condition is violated. And so we're still going to talk about the normal condition a bit today. The T procedures can be robust against non-normality. So it's okay if we don't have a perfect looking normal curve. If the graph of the data is single peaked, like they're all just lumped together, it's going to be good enough for us. It doesn't have to look like it's perfectly normal on each side. It's got to be without strong skew, though. If we see strong skew when we graph the data, that's an indication that the population has a strong skew, and therefore we'd have to have a sample size big enough for the central limit theorem to kick in. But if we don't see that strong skew or outliers, we can verify the normal condition. Let's go to page 2, people. Enjoy the view of the clipboard. All right, here we go. However, the presence of outliers, we can't get away with that. If we have taken a sample size and we can't use the central limit theorem, that means that our sample size is less than 30. And if we see an outlier when we have less than 30 data values, that's kind of a hint that the population is not normal, right? Or strong skew, those definitely, those two things, strong skew or seeing a pretty good outlier, those restrict us from verifying the normal condition. So basically, when you're going to do a write-up for this test for the population mean, mu, and you're using an x bar, if n is less than 30 and you can't use the central limit theorem, you should definitely include a graph of the data in your paragraph when you're checking your conditions, whether or not you feel the condition is verified. Okay, so if you're given the data, you're going to put it in L1 anyway because you got to find x bar and the sample standard deviation. So just quickly do a histogram And it doesn't have to be a great graph. You don't have to scale the axes and all that. Just do a sketch so I get a feel for what it looks like. So let's graph some data and make some decisions. Good practice for us. Graph each set of data and comment on the large normal count condition. Here's what I think we should do. I'm going to stop the video. What I want you to do is go to page 536, take that example, and just put the data in L1. And then I want you to go to number 2 here. On page 47, I went all the way back to chapter 1 to find this one. Put that data in list 2. And then flip over and go to page 543 and put that data in list 3. And then what we're going to do once we have all those is we're going to view and sketch a histogram, a box plot, and a normal probability plot, and then we'll talk about whether or not we could verify this condition. Do that now.